One question was left open at the end of the last video. How big can a neural network actually get, and what does it take to train something that large? Here's the strange part. The answer already existed in 2012. It had existed since 2006, sitting inside millions of consumer graphics cards built to render video games. Nobody in AI research had gone looking for it because nobody had a reason to. By the end of this video, you'll understand why the machine that finally trained the network you already know about wasn't built for AI at all, and why timing, not just capability, decided when the shift happened. Plain machine. AI in plain English. We're tracing the complete history, from the very first idea all the way to the present. Let's continue. To understand what changed in 2012, you have to understand what a processor is actually good at and what training a neural network actually asks of it. A CPU, the main processor in almost every general-purpose computer, is built to do one instruction, then the next, extremely fast, in careful sequence. It's a specialist in doing complicated things one at a time in order. That's exactly why it's so good at running an operating system or a word processor or almost anything you do on a laptop. Those tasks are mostly sequential, one decision leading logically to the next. Training a neural network is nothing like that. Remember the diagram from earlier in this series. Layers of nodes, each connected to the next by a weight. Training one means running the same simple calculation, multiply, add, compare, across millions of these connections over and over for every example in the dataset. It isn't one complicated task done in order. It's an enormous number of identical, simple tasks that could, in principle, all happen at the exact same time. Picture the difference this way. A CPU is one extremely skilled worker handling one task after another with total precision, fast but strictly serial. A different kind of chip is thousands of much simpler workers, each doing a small, repetitive task all at the same moment. For most computing tasks, one skilled worker beats 1,000 simple ones. But for a task that's actually thousands of identical, independent operations, which is what training a network's math really is underneath the diagram, the 1,000 simple workers win, and it isn't close. That chip already existed, it just wasn't built for this. The chip that would eventually train the network you already know about wasn't designed with any of this in mind. It was designed for video games. Rendering a 3D scene means calculating the color, lighting, and position of millions of pixels every frame, dozens of times a second. And every one of those pixel calculations is independent of all the others. You don't need to know what's happening to pixel 400 to calculate pixel 401. That's the same shape of problem neural network training turned out to be. Millions of small, independent, simultaneous calculations. Graphics card manufacturers had been building chips shaped exactly for that kind of workload since the 1990s, chasing sharper video game graphics, with no relationship to artificial intelligence research whatsoever. Two industries were solving structurally identical math problems for completely unrelated reasons for over a decade without ever meeting. In 2006, the maker of those chips released a toolkit called CUDA, a way for programmers to write general-purpose code that could run on a graphics card, not just render graphics with it. The reasoning was about selling more chips for more use cases, not about neural networks specifically. A small number of researchers in scientific computing Physics simulations, weather modeling, fields that also needed millions of identical calculations run in parallel, started experimenting. Neural network researchers were a much smaller, much less funded corner of that same curiosity. A few papers in the late 2000s tested training small networks on this hardware and found the same result each time, dramatically faster, sometimes by an order of magnitude, on exactly the kind of repetitive math that training a network requires. The tool had been sitting there, openly available, for 6 years before anyone connected it to the field's actual bottleneck at meaningful scale. So why 2012? Because that's when the dataset, the algorithm, and the hardware finally sat in the same room at the same time. Backpropagation had existed since 1986. The 14 million image dataset from the last video had existed since 2009. CUDA had existed since 2006. Each piece had been sitting, mostly separately, in different corners of research for years. The network that dropped the field's error rate by 10 points in a single year, the one you already know from the last episode, ran on 2 consumer graphics cards, using that same toolkit over about a week. Not a new invention, a convergence. 3 separate mature pieces meeting at once, each one necessary, none of them sufficient alone. Now, here's what this actually means if you work with AI tools or make decisions about them. Scenario 1. Your organization is evaluating whether to build an AI capability in-house or buy it from a vendor. The conversation usually centers on the model, accuracy, features, the demo. It rarely centers on the infrastructure underneath it. What hardware was this trained on? What hardware does it need to run? And what does that cost at the scale you actually operate at? A capability that looks affordable in a pitch can become extraordinarily expensive once you account for the compute it quietly requires. The same way this field's own solution sat unused for 6 years because nobody had connected it to the actual cost of scale. Scenario 2. You're told a new AI capability isn't possible yet or is a few years away. This episode should teach you to ask a more precise question. Is that a limitation of the idea or a limitation of the hardware currently available and affordable to run it? Those are very different kinds of not yet. Sometimes the idea is sound and the field is simply waiting, the way neural networks waited 26 years for backpropagation, then 6 more for cheap parallel hardware, for cost and availability to catch up. Recognizing which kind of gap you're looking at is the difference between writing something off permanently and correctly predicting when it becomes viable. The lesson underneath both scenarios: a good idea and a working idea are not the same thing, and the gap between them is very often an infrastructure question, not an intelligence question. Trace the whole line one more time. 1958, the perceptron. 1969, Minsky and Papert prove its ceiling. 1986, Rumelhart, Hinton, and Williams solve how to train a deep network. 2009, a dataset solves what to train it on. 2006, quietly, in a completely unrelated industry, the hardware that could actually run all of it at scale. 2012, all 3 meet at once, and the field changes in a single year. Here's the tweetable version. Backpropagation could train a network. ImageNet gave it something worth training on. Neither one could scale past a certain size because a CPU does one thing at a time, and a neural network needed to do millions of things at once. The GPU didn't make AI smarter. It made AI's ideas finally fit the hardware that could run them. Act 3 is nearly complete. The architecture could learn, it had something to learn from. Now, finally, it had a machine built to keep up. 3 ingredients, 3 separate timelines, 1 convergence. The algorithm, the data, and the machine to run them all met in 2012, and neural networks stopped being an interesting idea researchers argued about and started being something that worked, provably, at scale. That leaves one more question before Act 3 is done. Now that the ingredients were all finally in place, what actually changed? What does deep learning mean? And why does 2012 mark not just one good result, but the start of everything that followed? That's video 13, Deep Learning, the episode that closes out this act. Subscribe if you want the full arc. Each video in this series builds on the last. The AI glossary is in the description. 30 terms, plain English, free. This is Plain Machine. Thanks for watching.